There we go. All right, so let's go over this. So we're asked to explain why the following set is linear and then find the equation in terms of y, y in terms of x. So if we want to check that this is linear, we'd have to figure out what the change in y over change in x is doing. So essentially most of our change in x's are 2, but we have 2 of them that are 4. And then if we check out what the y's are doing, it's going down by 3, down by 3, down by 3, down by 6, down by 3, and down by 6. You also want to be careful. I saw this a couple times on the quiz, I think. Be sure to keep track of the sign, because if you're not keeping track of the sign, your slope's going to be off by a sign. So we have -3 over 2 versus -6 over 4, which reduces to -3 over 2. So our slope is going to be -3 over 2. So this is linear because it has a constant slope of -3/2. And then if we want to find the equation, that's when at this point we have the slope. We just need to pick one of the points to find our y-intercept. Actually, we're given our y-intercept here, but I'll do both ways. So we're technically given our y-intercept here. It's technically 0, 5, because remember, if you're given the point where it's evaluated at 0, then you have it. But say you didn't recognize that right off the bat and you just were going through doing it by hand, and say you picked this first point. So we would have 14 equals -3/2 times -6 plus b, and I didn't write this down in my notes, so make sure my arithmetic's right here. It's going to be 9. Subtract 9 from both sides, you would get that b is 5, which hopefully we would, because that is what the given y-intercept is. So our equation would be -3/2 x plus 5. And if you use that with any of the other points, -4, 11, -2, 8, and so on and so forth, you should get the same b value of +5. Questions, concerns on the warm-up before we go through these notes? I also want to give you one last reminder. I'm usually not going to give you this many reminders, but this one's the first one. Remember, you have your homework due tonight. The second homework will be popping up later today, but that first one due by 11:59 p.m. today. All right. Just in case, let me just pop this back up. So we're moving on to a new section. We're finally done. Well, no, we're not quite done. It's going to keep coming back to us, but we finished the notes on linear functions, and now we're moving on to something called average rate of change. So say you have a function y as a function of t, so y equals f of t, then the average rate of change between x equals a and x equals b is the following. Change in y over change in x, otherwise known as f of b minus f of a all over b minus a. Now, usually you'll see average rate of change written in this f of b minus f of a all over b minus a language, but I did want to also link it to a change in y over change in x. Now, you may say to me, well, that's slope. That's what we were just doing for linear functions. And yes, but also no. So average rate of change is a slope. It does represent a slope. So let me put over here. Different from slope, how do I want to phrase this? Well, I should be careful with the word different. I'll try to explain it in a second. So different from slope because of context. And I'll try to explain it more once we get down to this first example. But essentially, slope is a word that is used specifically when you're talking about a straight line. Now, technically, this does have a straight line in its context, but average rate of change is used, note down here in this first example, I'm going to scroll back on this side in a second. But this first example, that's not a straight line. That is not a linear function, but we want to talk about the average rate of change between 2 points. So the average rate of change is often used in contexts where we don't initially have a linear function, and essentially what happens is the average rate of change turns out to be the slope of the line between the 2 points. So it does turn out to be a slope. It is a slope. And if that helps you remember how to find it, if you want to think average rate of change, slope are pretty much equivalent. They pretty much are. So anyway, f of b minus f of a all over b minus a. So say we have, oh, it's not showing up. Let me reshare. Can you see now? Cool. So I'll leave that up for like 5 more seconds in case someone's got to write it down. So, I also at the end of this, the units of the average rate of change are the units of y per the units of t, or x, or whatever variable it is, which is essentially exactly the same as the slope because it is a slope. So change in y over change in x, or actually, so I should have been careful. Our equation here was in terms of t, so I should have had a change in t instead of You can't hear me? I assume everybody else can hear me because no one else has yelled at me. So here's what we usually do for that. So if you ever pop in and you can't hear me, so if you like see stuff being written on the screen and you can't hear me, either yell at me, but I'm unmuted, so that's not the issue. But otherwise, pretty much what I just told her, if you can't hear me and you're pretty sure you've told me that you can't hear me and everybody else can hear me, leaving the call and coming back in can sometimes work. Can you hear me now? Hello? And then I just babble to make sure you can hear me. Maybe? Can you hear me now? Like that Verizon guy? It was Verizon, right? I don't remember. Anyway. Hooray. Oh, you can hear me. Anna. 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 I don't know if she can hear me. Hopefully she can. Oh no! I don't have any more fixes. I have one last potential fix. 1 second. Not 2. Okay, Kate has a suggestion. I have one last suggestion that I could think of. I'm gonna keep going because I can't wait too long, but hopefully she gets that fixed. That's the other thing. Yeah, sometimes true. Oh, everyone's being so helpful. Okay, that's the last thing I can think of. So we're gonna try to move along a little bit here. So what are we looking at? We're looking at this function g x cubed minus 2x squared. Its graph is shown here. We're going to draw a line segment between the points on the function where x equals 0 and x equals 3. And then we're going to compute the average rate of change between that. So if I go ahead and plop 2 points on here at 0 and at 3, and I draw the line between them. So I've got the line between those two. And then if I want to actually compute the average rate of change, that would turn into a g of 3 minus g of 0 all over 3 minus 0. Hopefully she's going to get sorted. Anyway, so we would plug 3 into our function and then plug 0 into our function. Oops. Oh, my laptop is angry. Oh, man. There it goes. All over 3 minus 0. So that should give us, if you're writing anything you can't see it, interesting. Oh, well, I just unshared and reshared, so it did lag a little bit. My my Wi-Fi on my laptop popped out. But here we go. All right, cool. So if we calculate that out, we should get, essentially it comes out to 27 minus 18. That 7 should not be that small. And then essentially the back piece just turns in, ooh, I should be careful there. Should turn into 0. I should have had those parentheses there. And then divided by 3. So we'll end up with 9 over 3 is 3. So the average rate of change, which I will almost always abbreviate as average ROC because I'm lazy, but the average rate of change here is going to be 3. So essentially, what this means is the slope of the line between x equals 0 and x equals 3 is 3. So the slope of that line that we drew over there is that average rate of change. So the average rate of change is technically a slope, but it's used in a larger context because we can use it. We use the words average rate of change even if we're not talking about a linear function. Questions, concerns on that? That's how I calculate it. Hopefully not too bad there. I'll leave that up for like 5 more seconds before I scroll down. All right, so let's do a couple more. So now let's consider the function 1/16 x to the 4th minus x squared, which is graphed there as well. We want to evaluate the following and then interpret each as the average rate of change of g of x over some interval. So there's not a ton of space here, so I'm going to be kind of careful. I'm going to kind of immediately jump to the numeric answer. Actually, on this first one, I'll write it out. I'll write it out kind of up here. So remember, if we're doing this, we're plugging in, each of those numbers, and we want to be careful here. So let me like block this off. And then we would have, 1/16 -2 to the 4th minus -2 squared all over. So this is getting a little squished in here, which is why I wasn't originally going to write this out, but now I've committed. All over 0 minus -2. So I know that's really squished. So that essentially turns into 0 minus -3 over 2. So now I'm just gonna write this for the rest of them, but that's how you would find it, is you plug them into that function that we're given. I do want to be very careful. Make sure to try to include parentheses. Let me just trying to write stuff down so she can also kind of know what I'm saying. So those parentheses are really important. If you don't have those, then if you punch that into your calculator, it's going to tell you the wrong answer because it's not going to distribute that negative. Okay, I'm sorry. Mine's not lagging, so unfortunately that's probably on your side, which is not, I'm not blaming. That's just, it's your internet. I'm gonna stop talking. Sorry. So we'd end up with 3 over 2 as our average rate of change. So this would be the average rate of change between 0 and -2. So that's what that would be representing, is the average rate of change between 0 and -2. Is anybody else's lagging a lot? Mine's not lagging. I have it on multiple screens. I try to keep track of that. But if it's lagging for anybody else, I can try to pause more. No? Okay. So that's how you would calculate the average rate of change for that one. If we do the second one, okay. If we plug in -2, we essentially just found what we plugged in -2 in the last one. It turned out to be -3. And then it speeds up. Okay. I'll try to slow down a little bit as we go along to make sure everyone can catch up along the way. And then if we plug in -4, I'm not going to write out the whole hoopla again because I don't have the space. But if we plug in -4 to that function, we're going to get 0. You can also kind of see it on the graph. So if we look over at -4, it's over at 0. So you can also kind of use the graph to help recognize what these points should be. And then -2 minus -4 would essentially be adding. So we're going to end up with 2. So this would give us -3/2 as the average rate of change between -2 and -4. It doesn't matter which number you put first when you're saying average rate of change. Just kind of like with slope, it didn't matter which point you put first in the slope, as long as you were consistent. The same thing kind of happens here. You could say average rate of change between -4 and 2, and it would still be perfectly right. And then for our last one over here, we have g of 0, which again, we technically already found the value of when we were finding the first one. So g of 0 turned out to be 0. And then g of -4 also turned out to be 0. And so we'd have 0 over 4 is, of course, 0. And this is representing the average rate of change between x equals 0 and x equals -4. I don't know why I suddenly put the x equals in there. You could have said average rate of change between 0 and -4. Same deal. And then for part B of this question, we essentially want to take all of those expressions we just found and draw the line segment that it's representing the slope for. So let me kind of color code these. Maybe if you're colorblind, you won't be able to see it, but hopefully. So we've got between 0 and -2. And so we have the line between those two would be this one. So that would have a slope of 3/2, that line that I just drew. And then maybe I'll also change up the way I draw the line so that people can see it. So now I'll do a dotted line between -2 and 4. So -2 and, sorry, -4, -2 and -4 would give me this line here. So the slope of that line would be -3/2. And then I don't know how to change up the line again. I'll just have to do a straight line again. And then between 0 and -4, we have a straight horizontal line, which is why it makes sense that that has a slope of 0, because straight horizontal lines have a slope of 0. So again, even though this is a nonlinear function, we're essentially creating these lines to talk about the slope of the line between those 2 points, which is also called the average rate of change. Questions, concerns about that question before we move on? We're going to do a couple more. All right, I'll hold on a couple seconds in case people are still taking something down. All right. Compute the average rate of change for 2x squared on the following intervals. So notice, first of all, that these intervals are listed in a bunch of different ways, and it's just that you've got different ways to write it. So in the first one, we've got between 0 and 1. So we would want to, I'm going to write this out fully, so let me like cut this off so that I don't run out of space. So we would have g of 0 minus g of 1 all over 0 minus 1. Again, if you put the 1 first, which actually I would probably usually do, but I was going with the way it was laid out, you're going to come out to the same answer. So if we plug in 0 to the function, so let me try to write it out in full generality this time. Let me just keep putting my brackets there. Technically, you don't need it here because there was no second term, but let me just be consistent and keep those around. So we would have 0 minus 2 over negative 1, which would give us negative 2 over negative 1, which would reduce to positive 2. So if you had done it the opposite way, you would have gotten positive 2 over positive 1. If we do the next one, we have an interval from negative 1 to 1, an interval notation, which is essentially just saying go back to negative 1 and go all the way up to positive 1. So this time I'll actually put the larger y value first, or the larger input first. Again, does not matter which way you put it, as long as you're consistent. So we have 2 times 1 squared minus 2 times negative 1 squared all over 1 minus negative 1. Let me be consistent with my brackets. So we'd get 2 minus 2 over 2, which would reduce to 0. So the average rate of change between negative 1 and 1 would be 0. So that would, if we were to draw this function and draw the line between those 2 points, it should be a straight horizontal line. And then from negative 2 to 4, same deal. And here I am putting the other one first. Again, doesn't matter as long as you're consistent with, and when I say consistent, I mean if you put the g of negative 4 first, then negative 4 has to go first. So we had 2 negative 4 squared minus 2 times 2 squared all over negative 4 minus 2. Be consistent with my brackets. We would get 32 minus 8 all over negative 6, which will reduce to negative 4, as long as my notes aren't lying to me. Yeah, because that would reduce to 24 divided by 6 yep. And these last two no longer have any numbers in them. So we're not going to be able to find a like full final answer. Well, we will have a final answer, but not like this where it reduces really nicely to just a singular number. Because essentially what we'll need to do here is we'll just have GA minus G of B all over A minus B. And how we would want to write that finally is we would want to plug those in. I wrote too big. Let me write that a little smaller so I don't run out of space. We would want to plug them into the function. And that's where you can leave it because there's nothing else you can do to simplify that. And in this final one, I'm going to put the A plus H first because I'm just not being consistent on which one I put first. But again, it doesn't matter which one you put first. I just want to do something very specific with this one. Why is that a B? So here we would have A plus H all squared minus 2 times A squared all over. Now notice what happens in the denominator. The denominator we have A plus H minus A, so it would just reduce to H. Now, if we were to expand out that numerator, we could definitely go a bit farther. Some more things would start canceling out, but I'm going to say let's not do that. Let's save us the time. We're not too worried about how that would reduce. The main thing I wanted to talk about was how that bottom reduced. This kind of format is going to pop up again in another definition in a couple sections. Any questions on how I calculated any of those? I'll talk about that at the end of class. So yeah, I will let you know. All right. So the amount that Mary drives changes from week to week, so the amount that she spends on gas also changes. However, she's calculated that over the last year, she spent a total of $1,450 on gas. 1,400, 1,450. I can't read a number on gas. On average, how much did she spend each week on gas? So if you think about it, if she spends $1,450 on gas in a year, and there's 52 weeks in a year, on average, 1,450 divided by 52, so dollars and 52 weeks would give that she spends approximately $27.88 per week. She must drive a lot. If nothing major changes, how much should Mary budget for gas for the next 3 weeks? Well, that would of course be our $27.88 times 3 weeks. So she would want approximately $84. So that one might seem like a kind of weird question. It kind of doesn't look like an average rate of change, and it's kind of setting us up for something we'll see in a minute. But it is technically an average. You're essentially taking the fact that she ends at $1,450 worth of gas and she started with 0 and she goes over 52 weeks. So it is technically kind of an average rate of change. It's just phrased a lot differently. So our next one though. So we have the speedometer in Jacob's car is broken. That's not good. But on our way to the store, he was able to measure the distance from his house once per minute. So he was very purposeful and stopped every minute. The table below shows these measurements. So the time in minutes and the distance is going to be in feet. So what is Jacob's average velocity between the start of the trip and 3 minutes in? So one thing I want to point out very quickly before we do this one is the phrase average velocity. So average velocity, oh, that's not where I was drawing that. Average velocity is the exact same thing as the average rate of change of distance. So instead of saying what is Jacob's average rate of change for the distance between the start of the trip and the 3 minutes, they just say average velocity. So if you see the phrase average velocity, think average rate of change. It's just in terms of this distance function. So we want to know from the start of the trip, so that would be t equals 0, and 3 minutes in, so t equals 3. So we essentially want the average rate of change between 0 and 3. We don't have a function name here. I'm going to name this f of t, just so I can write what I'm about to write. So we essentially want f of 3 minus f of 0 all over 3 minus 0. So in this case, there's nothing to plug in. We just pull the values off of the table. So we have at 3, we're at 3,300. And then at 0, we were at 0. So 1,100. And let's pull out our units for this one. Let's be careful with putting our units on this one. So remember, it's always the change in the y values over the change in x's or whatever variables you're working with. And if you think about it, you can just kind of keep track. So the values up here are all in feet, and then the values in the denominator were in minutes. So the units of this would be feet per minute. And then what about between 2 and 3? So that's essentially going to be the same thing we just did, but with different values. So f of 3 minus f of 2 all over 3 minus 2. So we've got our 3,300 minus 2,600 all over 1. Which reduces to 700, so 700 feet per minute. So same idea, just a table now instead of a function. So we don't need to plug anything in, we just pull things off. And again, the main also I can't talk today. The other main thing is to recognize that average velocity is just an average rate of change. Questions, concerns on those two before I scroll down? All right. I'll wait like 5 more seconds in case someone's still writing something down. All right, so continuing this problem though, we're going to plot all of the data points on the graph, and then we're going to figure out between which two of data points is his average velocity the largest, and what about the smallest? Plot the lines between these two pairs of data. So we have, I'm going to set this up where each of the t-value lines is going to be up by 1. And then because we need to go all the way up to 7,300. Now we're going to go slightly off of this graph because it's just going to make it easier. We're going to make each one of these lines go up by 1,000. And so our last couple points will be slightly off the graph, but trying to make the lines any grosser value is, I think, going to be more difficult than just going slightly off the graph. So I can't really scroll back and forth. Can I like zoom out real quick and can I get it in there? It's gonna zoom out pretty far, isn't it? That's good enough. I'll zoom back in a second, but just so that we have the table in case you're also working on a thing you don't have it in front of your face. So we have 0, 0. So that's kind of nice. It's just the origin. And then we've got 1, 2200. So just above that 2. Nope. Just above that. Excuse you. Yeah. Just above. There we go. Good enough. 26,000, so just about a little more than halfway between the 2,000 and 3,000. 3,300, so just above 3,000. And then all of a sudden we're at 6,200. So at 4, we're just above the 6,000 mark. And then 7,000, so we're right on the edge there. And then these last two are just slightly off the graph here. So whenever you're graphing things like this, I don't often ask you to graph by hand, but just, get them as close as possible. As long as it's relatively looking correct, it'll be all right. And if we connect these in kind of I kind of missed that last one. I don't like that. Okay. There we go. So I don't know exactly what's happening between these points, but based off of the points that we have graphed, that's the shape that I would probably assume it to take. So we want to figure out which two of the data points has the average velocity being largest. So average velocity, largest. And what you want to think about here is remember that the average velocity is an average rate of change, so it's a slope. So you kind of want to think to yourself, when is the slope largest? Between what 2 points is the slope the largest? And that would look like it's most likely between t equals 3 and t equals 4, because that's when we suddenly make that really large jump between the two of them. 0 to 1 is also a pretty steep jump as well, but the one between 3 and 4 looks like it's probably going to be a bit steeper. And then average velocity smallest is, again, you think about the slope. If you were to take slope between 2 points here, which two would have the smallest, the least steep line between them? And I would personally guess, now we could also find this actually legit, but we're kind of just basing it off the graph and taking a good guess. I would guess between the 6th and the 7th one, because those were two very close together. And they also weren't that far apart on our table. Notice it only was a change in 100 and everything else was a change in larger than 100. So that's the way to triple check it. But most likely between, and actually, t equals 6 and t equals 7. And so if we wanted to draw the lines between those two, so let me take the largest one. I'll do that in green. So that was between 3 and 4. So we have this pretty steep line there. And then I'll do the smallest one. I'll dot it between 6 and 7. We've got this really not very steep line. Whoops, that's weird. Between those two. Oh, stop drawing in the wrong part. Questions on why those two seem to be the largest and the smallest values? All right, and then the last thing is that we're actually asked, using your answer from part C, so we're using the T3, T4, and then T6, T7, what actually is the highest and lowest average velocity? So if we start with the largest, well, that would essentially be our f of 4 minus f of 3 over 4 minus 3, because that's where we found the largest slope, looked like it was the largest slope. So if we go back to our table, I'm not going to scroll up, but if we go back to our table, f of 4 was 6,200. F of 3 was 3,300 over 4 minus 3. So we will get 2,900 over 1, so 2,900 feet per minute. So his largest average velocity was 2,900 feet per minute between the 3rd and the 4th minute. And then the smallest, I kind of already pointed out, was f of 7 minus f of 6 all over 7 minus 6. So it was the 7,300 minus 7,200 all over, 7 minus 6, which was just a change in 100. So those values were all just pulled off of the table. I just didn't scroll back up to have us look at the table. Questions? Concerns? On that question? Or about average rate of change, because we're about to go to a slightly different topic for the last couple minutes. All right. I'll wait a couple more seconds in case anyone's writing something down. Okay. Changing gears just the tiniest bit. A new definition: when a quantity P changes from P naught, so if you ever hear me say P, I never remember if it's an A or an O. I think it's an A. If you ever hear me say P naught, that's what I mean. I might also say P sub 0, but usually I default to P naught. So if it changes from P naught to P1, we define something called the relative change to be the following. It's P sub 1 minus P naught over P naught. So essentially it's the end value minus the beginning value. And this is like over the beginning value. And that's how I actually remember it. I usually say to myself end minus beginning over beginning instead of P1 minus P naught over P naught. But whichever one makes you remember it. But you just need to be careful. It's always the end value minus the beginning over the beginning. A lot of people will get it mixed up and they'll have the end value in the denominator instead, and you just need to be a little careful there. I'm going to erase this P naught. But that's relative change. And this is essentially telling you how a function is changing at that time. In a way, it's not very often that we'll be kind of interpreting it in any means, but this is what it is. Also, these are essentially unitless. And it's also usually written as a percent. So we get an answer and it's not in a percent, and we'll usually switch it over to a percent, but it's essentially a unitless thing that's just telling us how the function is changing at that time as a percent. So if we look at this first example here, so in January of 2017, some YouTuber X had 1.5 million YouTube subscribers. Today, the channel has 2 million YouTube subscribers. What is the relative change in the number of YouTube subscribers of YouTuber X based off these two data points? So we need to be careful to differentiate between the beginning value and the ending value. So they start, just to be super clear, they start at the 1.5 million, or that's where we're taking it to start. And we're taking the end value to be that 2 million. Now, since they're both in million, whoops, it's lagging. My laptop got angry again. Doop, boop, boop, doop, boop, boop. There it goes. Okay. So starting at 1.5, ending at 2. And since they're both in million, we don't actually have to write out a bunch of zeros. If they were different, if like one was 2 billion and the other one was 1.5 million, then we would need to be careful. But here they're both the same, so we don't need to worry about it. So we have our ending value of 2 minus 1.5 divided by 1.5. Punch that sucker into a calculator. You'll get 0.3 repeating. Now again, we will technically usually turn these into a decimal, so I'm going to take this to be 0.3333, and then I'll cut it off there. And if you forget how to change something into a percent, you're going to take that decimal point and move it 2 spaces over to the right. So this is going to change into 33.33%. And since it's positive, we can also say it's an increase. So I should be clear, you wouldn't say that it has a negative. So if this was a negative, you would turn it into a positive and say that number decrease. You wouldn't ever say like a -5 decrease, because that would technically actually be an increase. But since it's positive, we would say that essentially what it means is that there was essentially about a 33% increase in their subscriber count. So let's do one more of these. I think there's 2 left, but we'll just do, well, we'll see what we get when we do this next one. So I love these questions. During the first week of the semester at Evil Public School, the enrollment of Nina's business calc changed from 130 to 162, while the enrollment of Cortex's business class dropped from 18 to 8. Which class had the higher relative change in magnitude? So if we're looking at Nina's first, so it started at 130 and went up to 162. So it's always end minus beginning. So we have 162 minus 130 divided by the starting value. So end minus beginning over beginning. That's going to result in 0.246 or 24.6%. And then we have Cortexes that started at 18 and dropped to 8. So the end value is 8 and the starting value is 18. So you do need to be careful. I see a lot of people also just putting the larger value first. You got to make sure it's the ending value minus the beginning value. So here we have negative 0.55, or essentially a 55% decrease. So let me come over here and say increase over here. So that's what I mean by sometimes you'll drop the negative when you write your answer if it's a negative thing. So the negative gets sucked up, if you will, in a decrease, in the word decrease. Technically, negative 55% increase would be quote unquote correct, but everyone in life would look at you really weird. So if it's ever a negative result, you would just say it's that percent decrease. Anyway, but we're caring about magnitude. So since 55 is greater than 24.6, put our answer down here. So just to clarify, since 55 is greater than 24.6. So Cortex's has the larger relative change. Relative. And I'll just put in magnitude to clarify that that's the reason. I know it's a negative value, but when we're just considering the magnitude, we're just comparing the 55 to the 24.6. So we'll leave this last relative change change question to Wednesday, but let me babble about your quiz real quick and I will type it out in chat. So your quiz on Wednesday, let's see, what do I want to put on there? I definitely want to put on finding a linear equation. So we kind of did one of those as a warm-up, as the warm-up today, where I gave you a set of data and then I asked you to find a linear function from it. You won't necessarily have to determine if the data is linear. I will just tell you, here's some linear data, find me the equation. And then some average rate of change questions as well. I won't give you any relative change questions, but finding linear equations and average rate of change will be your two main things for the quiz. So that's in chat. Sometimes my chat is super laggy, so let me write it here too. So finding linear function and average rate of change for the quiz on Wednesday. So yeah, we've technically got 1 more minute, but we're done. So if you have any questions, feel free to stick around for a little bit. Otherwise, remember you've got your homework due tonight. The next set's going to pop up today as well. And we've got our quiz on Wednesday, which you now will know what it's on. And have a good day, and I'll see you on Wednesday.